Do you have any questions about stems? Mm-hmm. Yes, precisely, because what example? But actually, in any example, it works this way. We can construct some path integral that is written in terms of this uh, basic fields which are used to represent the fields in the CFT, and then construct, for example, Cosmode currents in terms of these fields. Is it well, the question? Or uh, or at least it will be some part of the theory, because in principle there can be other fields. Uh, uh, and concerning this field realizations, let me tell about this a little bit. Uh, so, what do we know now? That there are such Cosmode currents which can be realized as psi alpha of z, psi beta of z, normally ordered. Or it is the same as such a normal ordering, because this fermions have only the first order pole in the OP, and it can simply be removed. So there is this realization in terms of fermions, but at the same time we have Bosonisation and fermionization for the fermions. Mm, but here we have several species of fermions, so this Bosonisation formula should be a little bit modified. Uh, so do you remember the formulas for one component boson fermion correspondence? So if you have psi star of z and psi of z, how to express them in terms of free boson? Mm, yes, e2 I phi, and this is e2 minus I phi. So if you try to do it in the multi-component case, we can, so namely we can try to do the same. So before this, let me write this expression in components. So this phi is the following sum. So we know that I d phi, now maybe better to write I phi in the following sum. It is some operator q plus G0 log of Z plus sum of Jn over minus sum of Jn over n Z to the power n different from 0. Now, if we take derivative of this, we get this current J of Z. So, and here we have an extra operator which is zero mode of phi. So if this operator is something like a momentum of this zero mode, this one is it's a dual variable. So they're canonically conjugate in this sense. And if we use this expression to write it to I phi, we'll have formulas like this. On the right, we have sum over negative ends, sum over positive ends, and we have some ordering of this two guys. So e is e to the q, z to power j0. And the same formula for psi. Oh, maybe I can write it. So if you want to write it, are there any questions about these formulas? Yes. If you want to write such formulas, also since we have such commutation relation, then it is clear that this shift operator e to the q acting on some state alpha gives us the state alpha plus 1. So this one was one component, Bosonisation and fermionization. If you want to switch to n components, then naively we can try to take the same formulas like psi star alpha equals to minus sum over n less than 0 j alpha n over n zn sum over n greater than 0 j alpha n over n zn e to the q q alpha z to j alpha 0. And if we do like this, we will have the correct OP between psi star and psi. Since psi star alpha of z, psi alpha of z will actually be 1 over w will be 1 over z minus w. But there is a problem. This psi is a fermion. So the modes of psi star should anti-commute. But if you write formulas like this, these fields are independent, and because of this, psi stars with different alphas commute instead of anti-commuting. And there is a trick called Jordan-Wigner transform which can fix this problem. Namely, we should add here minus 1 to sum over sum from beta equals to 1 to alpha minus 1 and j alpha 0. And the same formula for psi beta, for psi alpha. Yeah, so it's j beta 0. So pictorially it can be written like this. So we have some lattice with nodes. Maybe let me draw it here. We have some lattice with nodes labeled by alpha, 1, 2, 3, and so on, and and we have some field that corresponds to some node or of some number. No, for example, 4. So it can be written like this. So there is this field itself. It lives at this node, and there is some operator which lives on all previous nodes. And this operator anti-commutes with, so it commutes with everything except this shift operator. So it so it anti-commutes with the shift operator, because the shift operator shifts one of these currents. So and if you consider here, for example, psi 2 star, it will look like this. So when we try to compute the anti-commutator, we need to permute this field within this operator. So and when we do this, we change sign. If you consider two operators on the same side, then the tails just cancel. If this operator is somewhere further away, then the same phenomenon happens, but with this tail of this operator. So we can say that as a result, psi star alpha of z psi star beta of z on the commutator equals to 0 for alpha different from beta. And all this works for all operators. Are there any questions about this? Yes. Uh, uh, I don't know. Maybe it would be more correct to say that it is a Jordan-Wigner-like transform, because Jordan-Wigner transform is literally for different operators, but it is ideologically the same as this one. So Jordan-Wigner is for the transformation between sigma matrices and fermions. So, with e to q alpha. So e to q alpha anti-commutator with -1 to j alpha 0 uh, is equal to 0. Because it shifts this it should the eigenvalue of this operator by 1. So in the Jordan-Wigner transform is precisely this idea that if you want to change mutual statistics of the two fields, we can add this non-commuting anti-commuting tails. And this is purely two-dimensional phenomenon, because if it is in higher dimensions, we cannot draw such tails connected to, like, they will be one-dimensional, but and there will be no linking number between one-dimensional operator and the zero-dimensional, between one-dimensional and zero-dimensional operators. So, and this is actually why there is no distinction between bosons and fermions in one dimension. So, their statistics can be changed in this simple way. Yeah. Is it fine? Yes. Now we can combine Bosonisation with this fermionic realization. So let us first check what happens when alpha equals to beta. So j alpha alpha will equal to e to the I phi alpha of z e to minus I phi alpha of z. Well, let me first write the OP. of these two fields. So it will be 1 over z minus w e to the I alpha phi alpha of z minus phi alpha of w. And if we expand this, have 1 over z minus w plus I d phi alpha of z plus higher order terms. So we conclude that j alpha alpha equals to j alpha. Well, you can write I d I d phi alpha. And if you go to off-diagonal fields, then almost everything commutes. Actually, I forgot. No, to get correct OPs without any extra signs, this should be put here in the beginning. Yeah, right. Then when we multiply such operators on the same side, for example, the tails can cancel. Okay, but in this product of two exponentials, the tails cancel. How to say it? So if I multiply such two operators, we will only have the part of tail between the operators. So in a sense, this part will cancel. So you can write that j alpha beta is maybe with a minus sign, but it doesn't matter. E to I phi alpha minus I phi alpha of z minus e to I phi beta of z, and this product of minus signs. So gamma equals to, I think, beta from alpha to beta minus 1, something like this. And this j alpha alpha can be written as j alpha of z. So there is this Boson realization. don't have any questions. Oh, and let us consider some particular case, namely the case n equals to 2. Well, in this case, we have just two fields. Oh, let me think. Yes, so there is phi 1 and phi 2, but we can also introduce the sum and difference. Namely, we can introduce phi plus equals to phi 1 plus phi 2 over square root of 2, and phi minus, which is phi 1 minus phi 2 over square root of 2. And now let us first write this J11 and J22 in terms of phi plus and phi minus. So probably like this. And of diagonal currents will depend. Ah, yes, thank you. Uh, yeah, and also factor of phi. Deal of this. Yes, thanks. Oh, times some minus sign, which is in this case in essential. It will be in essential. So this is the main phenomenon that this field phi plus enters only into the diagonal currents, and we can easily remove it by considering only J. J12, J21, and the difference of J11 and J22. So, yes. So to head at the level 1 is generated by J11 minus J22, which we can call H. J12, which we can call E, and J21, which we can call F. So, this Bosonisation gives the following formula: H equals to I square root of 2 d phi minus E equals to e to I square root of 2 phi minus F equals to e to minus I square root of 2 phi minus. And now we will check the LPs to verify that it is actually our algebra. But you see the idea that simply changing the number in this exponential that changes the dimension of this field brings us from free fermions to cell to head. So it's a completely different algebra. So let us check its OPs. So U of Z with f of W is e to I square root of 2 phi minus e to minus I square root of 2 phi minus equals of Z of W equals to 1 over Z minus W squared e to so the first term normally ordered. So the first term of this OP is 1 over Z minus W squared plus I square root of 2 D phi minus of W over Z minus W plus regular. So it is actually this H generator. And concerning the other OP, in principle, we know this already. Because it is the OP between the Yuan current and its vertex separator. So we can simply write that H of Z was F of W was E of W equals to by the way, to what? What should be the coefficient? Maybe I actually missed E and F. No, maybe it's fine. Mm-hmm. Yes. Hmm? Hmm? U W, right? So, so like this. Uh, uh, as I remember, uh, this SO2 at the level 1 has central charge 1, and it is realized in terms of fermion, in terms of free boson, which also has central charge 1. Because so it was written for the GLN case, and it mixes different operators. So I do not want to think about it, like how it interacts with phi plus, how it interacts with phi minus. I simply removed it and shown that the obtained algebra has correct OPs. Because, for example, the choice of the sign is not unique. We could do it some other way. So we could construct the tails in some more complicated ways, and said that this limit preserves everything. And I just want to show this. Mm, uh, uh, what else? So this circular bosonisation is nice because of the following observation. Dimensions of all these fields are uh, one. So in particular, dimensions of E and of F are one. And but these operators change the U1 charge of this field phi minus. So. We can ask about the action of these operators on the free bosonic Fock modules. So maybe how to say it better. So models which are present here, well, actually there are different sectors, but let us consider the one which corresponds to alpha equals to 0. So we have some. So let me draw some coordinate axes. So it is a value of j minus 0, and this is the value of L0. So we should include this Fock module. But since we have this operators, we also have Fock modules like this: square root of 2, 2 square root of 2, and so on. Minus square root of 2, minus 2 square root of 2. And the images are like this. So here it is 1, here it is 4, and so there are other Fock modules with different charges. But what is important that if we there is a representation of this SO2 one head. But what is important that is that we can look at this as at some representation of the Virasoro algebra. So there is also Virasoro algebra acting here. And we have some operators of dimension 1. And what is special about the operators of dimension 1 is that if we consider the LP, E of Z with P of W, then what will we have? Mm-hmm. Yes. No. There is this case that T of Z with E of W equals to 1 over Z minus W squared E of W plus dE of W over Z minus W. But if you expand the other way, it gives simply E of W. So it means that zero modes of E and of J commute with L0. But in principle, it was clear even before, because there were zero modes. No, maybe no. It needs some computation, but and now we see that LNs commute with zero modes of zero modes of F. By the way, such operators with dimension 1 are called screenings. So they commute with the action of the Gauss algebra, and they change this. They change. Uh, 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 they want charges. Hmm? Screenings. Hmm. Or scanning operators. So, since they commute with the Gaussian algebra, we see that here we have f0 that sends this vector, some vector in this Fock module, some f0. There is also f0 that sends this vector to this vector in the Fock module. And since this operator commutes the action of the Gauss algebra, we know that f0 acting on the vector square root of 2 is the highest weight vector in this Fock module. So how 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 shall we call it? Actually, it is a vacuum module because it is for dimension 0. And in the same way, f0 acting on the vector 2 square root of 2 is some highest vector in this Fock module. So highest weight vector. In so how to call it in this module M11, oh, and so on. So this is the following phenomenon that there is this vacuum module. It contains some submodule that goes from this highest vector. But this submodule is itself not irreducible because it also has some non-trivial highest weight vector at the level 4. And there is this kind of Christmas tree in this C equals 1 theory. Yes, mystery of nested Rasa modules. And this so here it is a kind of exceptional situation that have some a large number of scanner's. For example, if we go to a generic SLN case, we will have like n times n minus 1 scanners. Which form some trivial algebra. In the general case, for in a sense, for arbitrary central charge, we will only have two independent sets of more or less n minus 1 screenings. No, not more or less, but just n minus 1 screenings. So, for example, for the Virasor case, there will be two screenings, e2 b phi, maybe square root of 2 b phi, and e2 minus square root of 2 b phi. No, e2 b phi, e2 b inverse phi. E2 square root of 2 b phi. So, and if we remember the definition of B, then on this one. So, S equals 1 case corresponds to B equals to I. And these two scanners coincide with this SO2 head generators. So what else do I want to say? We can also say about this representation of SO2 hat that it is irreducible since let me think. Since this representation is a unitary and mm, 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 let me think. Yes, it is reducible because it is a unitary, because this free boson Hilbert space has positive definite scalar product, and the mapping between, so this embedding of SO2 had the level 1 preserves this scalar product, and so it cannot contain non-trivial subrepresentations, and it also does not contain uh, mm, non-trivial factor representation, since we get the whole space, because we can get all the highest vectors simply by acting E or acting with modes of E and F on this highest vector. In a sense, we can get any shift of the E1 charge. So we get all these highest vectors, and we have a free boson inside our algebra, because it is the operator H of Z. So we can construct all these bosonic Fermat modules, and because of unitarity, they don't have any non-trivial subrepresentations. So, hmm? Hmm? Okay, let us write. So what was my mark? Uh, so mm, on this one. Because first, all highest vectors, mm, all highest vectors are in this representation. Maybe let me say it like this. This Hilbert space is an irreducible representation of SO2 so point one is that all highest vectors are in the same representation of SO2 hat. Simply because they all can be obtained from this vacuum vector. So square root of 2 can be obtained as E1 acting vacuum, square root of 3, 2 square root of 2 can be obtained by something like I think E1, E3 acting in vacuum. In any case, we can obtain at least some vector on this representation. Also, in each of these bosonic Fock modules, and then act with the free boson which is inside our algebra to get the highest vector. So. And second is there are no non-trivial subrepresentations. And this is because h of z equals to I square root d phi minus. And all bosonic, all Fock modules of the free boson are irreducible. Like all Fock modules with a given charge are irreducible. Maybe better to say let us give them some names. And this will be V0, this will be V square root of 2, V minus square root of 2. Because it's simply the free boson. Check. So is okay. And actually, we can construct another representation using the same technology. So here we only here we need to choose this charge or how to say it. Yes, so we need to choose the charge of this first bosonic Fock module in such a way that all these fields E, F, and H have integer modes expansion, because otherwise it will be some different twisted algebra. we will have different operators with different indices. But there is another option to choose this vector. So, namely, let us study all such possible choices and study the OP of E of Z with some E to I alpha phi. Alpha phi of W. So E is this one, so it will be Z minus W to square root of 2 times alpha, right? E to normally order. Phi minus. So we have SOP, and we already studied the case when alpha is n square root of 2, and it corresponded, so it gives us z minus w to power 2n. But there's this factor of 2, so in principle we can choose this n to be half integer. So we can choose alpha equals to 1 over square root of 2 plus n square root of 2. So we'll have in this case z minus w to n plus 1. So it is still integer, and we can also study this case. So the picture here will be like this, in the same coordinates. So here it will be 1/4. So actually we need to compute all these dimensions that correspond to such alpha. The delta of alpha will be 1/2 1 over square root of 2 plus square root of 2 squared. So it will be 1/4 plus n times n plus 1. So there will be two, so everything is shifted by 1/4, and maybe it's better to write this 1/4 here. So it will be 0.01/4. And there will be two fields with minus 1 over square root of 2, 1 over square root of 2, and there will be 3 over square root of 2 minus 3 over square root of 2. So, and so about dimensions, So there is this part of parabola, and the next dimension is 1/4 plus 2. So this will be somewhere. So 1/4, 1/4 plus 2, and 1/4 plus 20 equals to 2, 2, it will be 6, right? So there is, oh no, no. Ah, no, I simply did not draw this fields. On there are somewhere 5 over square root of 2 minus 5 over square root of 2. So there are these two representations, and they are called integrable representations. And they're called integrable because they are because there is this Kac-Moody algebra or affine algebra, but at the same time there should be something that we can call affine Lie group, which is obtained by exponentiation of this algebra. And it is in the same situation as for the finite dimensional Lie algebras, that we can that some representations of the algebra can be lifted to representations or the corresponding group, and this some cannot be. Because if you take a SO2 with some arbitrary spin, if you take some Fermat module of SO2 and try to make it a representation of the whole group, it does not integrate, because e to the 2 pi I h should, or depending on group, or 4 pi I h should act by maybe if it is h, then always e to the 2 pi I h should act by 1 in the Lie group, and in the algebra it does not act by 1. So here there are only two such representations which can be lifted to the representation of the whole group, and they are called integrable representations. Hmm? Uh, oh. Hmm? Yes, and there's this small difference in the action of center. So, in one case, we need only integer spins. In the other case, we can also have half integer spins. So it is spin 1/2, and this is spin 1. So, and we will actually see it now. Uh, Oh, we can write that there are representations of this group. So 2, 1. Okay, let me erase this. Hmm. So what do I want to say? Okay. So I wanted to see uh, how these representations look like. Uh, maybe maybe. Um, so let me. Let us actually talk about this fact about the integrability. Uh, so there is such thing as Cartan-Chevalier generators. Mm, Probably I will spell it wrong. Uh, mm, I need to check the correct spelling. But the idea is that we can realize, we can generate any algebra using some triples of generators that form so two subalgebras. And the rank of the Lie algebra equals to the number of such triples. Uh, so if it is just so if it is so and then the generators look like, and by the way, do you know this or not? Oh. So I don't know how they look like here or not. Mm-hmm. Okay. So let me just write them then. So if it is SLN, uh, mm, then there are these simple rules. E uh, 0, 0, mm, and their commutator. 1 minus 1. So basically E uh, E I plus 1, E I plus 1, I. So all such generators. Uh, and their commutator. E I minus E I plus 1, I plus 1. So these are called positive rod, these are called positive rod generators, and these are called negative rod generators. And if I switch to SLN case, to the affine case, we also add the generators. So this is a positive root, and we add the smallest positive root. We add a smallest negative root multiplied by z. So we also add this table. 0, 0, z, probably with positive power, 0, 0, z inverse, and the commutator. So in terms of our final algebra, it means the following, that positive roots, positive root generators are j, I plus 1, 0, and j, I, jn, 0, if it goes plus 1 or minus 1, actually, probably plus 1. Maybe it doesn't matter. So they are kind of transposed. I plus 1, I, 0, j, 0, n, minus 1. Hmm?
So to construct the affine algebra with additional generators with general
Here I wrote these generators in this representation with k equals 1, with k equals 0. They are just n-by-n matrices. There is no central extension. So it is representation. There I wrote this representation. I wrote the generators kind of in the loop group. So it is for so it is written for k equals to 0 on this representation.
Then sorry, what are J?
These two are I erased this, but these two are Lie algebra indices, and the last index is the M-mod index. Actually, let me think. Maybe problem is positive or negative, but it does not matter because anyway, it will be just some automorphism. So there are the generators, and let us compute their commutators. So commutators between different generators are, I think, yeah, they are 0. And let us compute commutators between in these triples. So commutator of j I plus 1 0, j I plus 1 I 0 will be j I minus I 0 minus j I plus 1 I plus 1 0. And for this affine generators, n 0 1, j 0 n minus 1. It will be k because there is a central extension. And different, so and this usual Lie algebra part plus j n n 0 minus j 0 0 0. Wait, I wrote 0, but we have only 1. We have indices from 1 to n. So 1 1 0. So there are this subalgebras. So and if you compute, so here we clearly see that that it is our original SO2 algebra, because well, it simply lies in that SO2 that was inside well, SLN, which was inside SLN head by design. It was just affinization of that SLN. But this algebra is also closed, because we can check that commutator of this K plus J and 0 minus J 1 1 0 actually, so with mm, J and 1 1 is 2 times uh, J and 1 1. Okay, simply computes with everything. So uh, and it is more or less clear that if we want to construct the whole algebra, such generators are sufficient, because first we want to construct all the generators with one at any possible place in this matrix, and with zero trace. We can simply commute such matrices and then such matrices. And if you want to add this powers of z, in a sense, to add all possible modes, we need to commute this matrix with all other matrices. So in this way, we can put z at any place in this matrix, and then we can commute such matrices to get the squared, and so on. So the point is that all these generators actually generate the whole algebra. And the only there are relations between these generators called Serre relations, which can be found somewhere, for example, in Wikipedia, but we will not need them for this simple analysis. So we see now what is the possible obstacle for this representation to be integrable. It might happen that even though representations of this Lie algebra at a level, this Lie algebra with index 0 is finite dimensional, but representations of such subalgebras are some Rama modules, and if this happens, then it means that our representation is not integrable. And in this case, we can check that this does not happen, because we have this parabola, and if we draw the action of this so if we draw the action of this algebra, then well, let me maybe introduce this generators for SO2, because we are thinking about SO2. So SO2 and the level 1. So there is a commutator of E with F equals to H and there is E0 F0 goes to H0, and there is uh, actually this notation is a bit inconsistent with what people usually use for the Lie algebras, but it is almost like that. So um, here it will be F1 with E minus 1 will equal to K minus H0. So let us draw the action of this E0 and H0 on this picture. So let us choose some point, for example, in this one. So E0 changes this charge by square root of 2, but does not change the dimension. So it is easier. F0 acts in the opposite direction. So it is F0. And this and this two operators change the dimension. So F1 acts like this. And and E1 acts like this. No, it will send us to this vector. So this is E minus 1. And we see the directions of this two subalgebras produce such straight lines of states. So it lands somewhere here. So it produces such lines of states, and since these lines are bounded by parabola, they always have two intersection points. So it means that all representations of these two Lie subalgebras are finite dimensional, because a parabola always intersects a line in 2 points, right? So yes, yes. I have just chosen some place to draw the section. Maybe it was better to draw some bigger picture. I don't know. So in some they always act like this. I have just shown how they change these two charges, dimension and the U1 charge. So Yes, because if their representation is infinite dimensional, it means that its highest weight is not integer, and so exponential of 2 pi I mm, h will not act by 1. So maybe I should write it somehow. Uh, so maybe let me write it here. So, so it's a kind of definition. So the representation of the Lie group uh, uh, e to the 2 pi I times cartan actually. So ei minus I plus 1 plus 1. Well, e to the 2 pi I of some of all these h's, including affine ones. So if representation is infinite dimensional, of this SO2 triple is infinite dimensional, maybe oh, should, then this is maybe let me write like this. Representation of is finite dimensional is equivalent to this, because if they're infinite dimensional, it means that highest weights can be different, and it does not exponentiate to 1. And also in the Varma module, even as with positive highest weight, I think it does not hold. But for some different operator, I think. But in this case, there is this argument that one action is horizontal, another this in the action of triple is 0 f0 h0, and this action, and this is the action of this other triple. This is e. This is E minus 1 F1 H. So it is not H0, it is K minus H0. And they always have this endpoints. So now I want to say that we have constructed just two such representations, but actually we constructed all of them for level 1. Mm. We have all integrable representations. Why is it so? Because let us take the highest vector. Uh, so let us take the highest vector and compute its norm. No, not highest vector, but let us take a vector that is killed by F1. We always have this because of this argument, for example, and because we don't have vectors with negative dimensions. Mm. So norm of this vector is v e minus 1 f v. No. Sorry, not of this vector, but of e minus 1 acting on this. So we have some vector which is killed by F1 and by one of these generators, and we want to construct a vector obtained by the action of e minus 1. So we use this commutator, right, that it is v k minus h0 v. So this should be greater or equal than 0. And if k is equal to 1, so we can write that a k is greater or equal than v and v h0 v. And if you look here, who is a vector which is killed by F1? Actually, Wait. Hmm? Oh, hmm. Oh, let me think. No, actually, I've drawn this picture in the wrong way. Actually, because this distance is 2, so in this goes here. Yes. So if we act on this vector with f1, it acts by 0 because there is it should land here, but there is no vector here. And so here the same. This f1 will act somewhere. Oh, so this f1 will act. Hmm, no, maybe it's. No, here is different. Here probably we should take a different vector. Hmm. No, wait. Wait, I've drawn this picture in the wrong way because mm, sorry. Uh, this picture and also other picture because it is it in the other way around. This if one decreases the eigenvalue of 0, so sorry. This is this action. Oh, it would be strange if it did not kill the highest vector. So, so this is uh, e minus 1, and this is f1. And and here this line should also be drawn in a different way. Sorry for such stupid mistakes. One. Right. And so this vector, which is killed uh, by f1, this one is also killed by f1. Basically, uh, if you have some representation on the top, here it is a two-dimensional representation, here it is a one-dimensional representation, then all vectors of this representation will be killed by uh, f1 because there are no vectors with smaller o0. So, and if you have some representation of high split lambda, then this v h0 v equals to ranges from minus lambda plus 2 to lambda minus 2 lambda. So means that k should be greater or equal than lambda. Lambda should be less or equal than k. So highest rate of this usual filter representation on the top level. And we constructed this representation with lambda equals to 1, and this representation with lambda equals to 0. So there is this two-dimensional representation here, and there is one-dimensional representation here. And we can also compute the characters of these representations. So character of this zero integrable representation. So and you can actually so we can uh, add two generators, one that counts the dimension, another one that counts U1 charge. So it will be 1 over the kind of q, which is q to 1 over 24, product of 1 minus q to the n. And here we will have a sum of q to n to n squared t to the to n. So it is a kind of theta function. Not kind of, but just a theta function. Theta 3 of of t squared, probably q squared over e of q. And for this other representation, for integer n's. So when we have sum over half integer n's, it's kind of theta 4. there are functions of two variables, um, q and t, but it is also possible to choose uh, some gradient that takes both variables into account. For example, so it will correspond to. For example, we might want to give this two generators the same gradient. So in this case, we should it is called principal gradient. So when degree uh, is zero uh, and f and f1 are the same, because they are kind of both positive roots. Uh, and if we want to compute these characters inside gradients, then we should put uh, t equals square root of q. So in the sense, is this uh, let me, oh, is it correct? So this one, uh, mm, so this one has a gradient. Mm, Hmm? I simply want this. Oh, this trace. Um, um, uh, so it should be some linear combination of. Let me say it like this. So we want that the action of some operator, some gradient of some operator uh, acting on a vector will be gradient of this operator plus gradient of this vector. So the idea is that we have some operator that change the eigenvalues of 0 and of j0, and we are computing this weighted sum of we are computing the sum of weights of all vectors in the space of some operator. So originally this operator is like this, but it can be useful to count all this positive and negative potential generators on the same footing. But here probably I'm missing something, or I made some mistake. But or maybe it's possible here to put just t equals to q to minus 1/2. So if you do like this, then this character will, so in this case, the weight of vector will equal to the number of applications of this positive or negative roots to get it from the highest vector. Oh, kind of assigned number. And this can be useful.
The square root exponent is one of exponent. It comes from the fact that increase the charge, increase the dimension by the
Hmm?
why
Which square root?
e equal to q to the minus one?
I'm simply adjusting the weights. In a sense, this operator shifts h0 by 2. This operator shifts h0 by -2, and L0 by -1. So I want to make this shift equal. Actually, I don't know. Should it be -1/2 or -1/4? Oh, but let us forget about this actually. So the point is that if you have this t that counts this A1 charge, then we have such theta functions divided by something. But if you choose some gradient to make this character function of a single variable, for example, we can just put t equals to 1. Then we get some theta constants divided by Dedekind eta, and these expressions are modular forms of something. And this is because like physically, this is because computation of a character is essentially a computation of some partition function on a torus, and we can apply modular transformation to this torus. So the only question is what happens globally. Like, do we go between different sectors of our theory, or do we have any homomorphic anomaly? So we see that this chi10 will go to itself if we do a modular transformation. I know actually it's tricky. It's trickier question because it is a theta function of q squared. But this one definitely goes to something different because this theta force is not invariant of the modular transformation. Okay, and do you have any questions? Right.
Whether it's b is still b, those minus lambda to lambda.
Because it is how the finite dimensional representations of SO2 look like.
Sorry, there is generic satisfy the.
Yes, yes. But here we ask this about this on the top level, on the ones that are killed by F1.
Yes, so but the one killed by F1 has a restricted. I mean, doesn't do not take all these eigenvalues, right?
Uh, no, it does, because if you look at the pseudo representation of this horizontal pseudo representation on the top level, we have all these vectors, and all of them are killed by F1.
Okay, just top horizontal.
Yes.
Also, I want to ask. So these are the two integrable representation if k is equal to one.
Yes, of course.
Here k is one.
Hmm. So, for example, if you take this SO2 realized as SO3 in terms of real fermions, we have k equals 2 representations. Actually, I don't think how they look like precisely, but it's a little bit more complicated than this. But probably we'll get all three of them, and we can prove that they're reducible in the similar way, because fermion is also so Fermat's Fock model is also unitary. So mm, mm. Okay, attention.